Are we set? Good. Okay, good afternoon. Welcome to our University of Tennessee Nuclear Engineering Colloquium series. I'm Wes Hines. I'm the department head here. Thanks to all the graduate students that participated in the poster session last week. We didn't have a seminar because we had the Advanced Reactor Summit here. If you had the opportunity to go over and visit the booths and visit the summit and listen to the speakers, I hope you enjoyed it. I thought it was a great opportunity for the university to host, such a prestigious group of nuclear engineering leaders, and I certainly enjoyed it. Okay, today we're lucky to have Dr. Richard Vasques. He's an assistant professor of nuclear engineering in the Mechanical and Aerospace Department at Ohio State. His research interests lie in the areas of particle transport theory, fission reactor physics, and advanced modeling and simulation. He's particularly interested in the mathematical and computational modeling of transport and diffusion processes in stochastic mixtures, with applications in nuclear reactors, nuclear imaging, medical physics, atmospheric sciences, and graphic design. Before joining Ohio State, Vasques held positions at UC Berkeley, University of Aachen in Germany, and the Federal University of Rio Grande do Sul in Brazil. He holds a bachelor's and a master's in applied mathematics from the Federal University of Rio Grande do Sul, and he has a PhD in applied interdisciplinary mathematics from the University of Michigan. And he received that as he attended Michigan on a Fulbright fellowship. Welcome.
Thank you, Wes. Thanks, everyone. Thank you. It's my pleasure to be here. It's my first time in Knoxville. I'm really enjoying it. So thank you for having me to your colloquium. I'm going to jump right into this. I was struggling where I should start this talk when I was writing it, chronologically speaking. So I decided I'm going to start around December 2015 when I was in Berkeley, and I got an email from Pixar Animation Studios inviting me to come down there to talk about my research and where that would combine with them. So this is me happy after I went to the gift shop at Pixar and the Luxo ball and there you go. The Luxo ball and the lamp that you all know. And the reason why I got invited was by Magnus running it. So that was my entrance little thing to stick on your chest. And he was interested in some of the work that I had done in non-exponential free flights. And just to situate here, that was the end of 2015. He had just finished working in one of the Pixar movies that had come out that year. So that year had Inside Out, that probably everybody saw. And it also had, if you had small children, you might remember this, the movie called The Good Dinosaur. And it was much more kid-oriented, but it made a lot of progress in the CGI area. So specifically, parts of that movie were so realistic that people were not sure whether they were CGI rendered or they are actually landscapes. So if you see here, this is one of those CGI images from the movie. If you saw the movie, you'll probably recognize at the bottom there is a little dinosaur. So this is a farm on the movie. But other than that, the landscapes are breathtaking. And the clouds and everything there is CGI rendered. Now, one of the things that he really advanced, Magnus, really advanced in the field that helped him get an Academy Award for technical achievement and the Annie Awards for this movie was specifically how you deal with clouds and how you deal with foam in water. So up until this point in time, every animated movie that you would see had the clouds in the sky drawn in by an artist in a software, and then they were put together and moved around by a software, but they're all hand-drawn or software-drawn. This was the first time that they actually did a full physical volumetric-based Monte Carlo code to generate all of the clouds. So all of the clouds in this movie, all of the fog and the foam are all generated by a fully physical Monte Carlo process. And the issue then became, if you go to the CGI community, how can you make this even more realistic? How can you make these clouds and this foam being more realistic and more efficient to model in CGI problems? Talking a little bit about CGI and how this comes to be. Back in 2011, this guy named Eugene Dion, who was at the time at Weta Digital in New Zealand. Weta Digital is the company that did the special effects for the Lord of the Rings movies. He found out about some of the work we were doing in nuclear engineering and kind of started branching and bridging the gap between CGI and transport theory in nuclear engineering. And then he wrote this book, which is available online, Hitchhiker's Guide to Multiple Scattering, which is very fascinating, the kind of stuff that they do with transmittance functions, very similar to the kind of stuff we are looking in. But they really worried not so much about how physically accurate it is, but how visually pleasing it is. So there's a lot of lessons to be learned between the two communities. And Magnus was interested in this, and specifically interested in looking into how do you deal with translucid materials. So if you have some sort of crystal structure that allows the light to penetrate and then come back out on the surface, or how do you render skin, for instance, as a translucid material? So we started looking into this subsurface scattering embedded participating media and how we could do some improvements in that based on the theories that we have for nuclear engineering and for nonclassical transport, which is one of my areas of research. So just to give you some background on CGI and basically what's happening, you have pretty much what you do, you set a scene, right? You have your surface, you have your material, you have your scene ready, and you place your camera or the eye of the viewer somewhere in the scene in your software, and you have some light source, might be more than one. And basically what you're following is the path between the light source gets some energy deposited in the surface, and your eye is seeing that is going to see that one particle. That's pretty easy to do. And that's usually what you do when you're starting in the little ray tracing programs to deal and to play with this. So some of these images that I'm going to show you now, I have a PhD student doing an independent study on ray tracing and CGI. And specifically, this is following a book that's also available online by Peter Shirley. It's called Ray Tracing in One Weekend. And then it has 2 more books after that. But here what you're doing is you're setting a scene and a very easy geometrical object. So I have 2 balls in there. One of them is green, the other one is glass. And all you know is this information where they are, where your light source is, and how light diffracts as it goes through the glass or goes through the green ball. And literally, what you're doing in this one is you're following the path of the photon from the light source to the material and then to the camera. But you're doing that the other way around, right? So you start at your camera, you shoot a ray up to the material, and you see if that ray reflects anywhere that has a point, a light source, and you get the energy deposited in there. In this case, you're starting to complicate your model a little. So I have a metal ball here that has a reflection of the green ball. So if I'm the camera, I shoot a ray from my eye into the metal ball, and I see, okay, can I trace a path from that point in surface to a light source? Yes, so I'm going to get some energy in there. But I also need to know if there is light coming from anywhere else into that point. So I have to shoot other rays as I get to that point and see if it hits something else. And if it does, like it hits the green ball there, I'm going to account for that amount of light being deposited in that point. And it might hit another point. And you can see how this is going to exponentially increase as I increase the number of rays coming out of it. So it gets step by step more complicated as you start looking into this. So here I have a glass ball and a metal ball. And this one is reflecting a lot of different things from the walls, from the glass. The light that comes from there goes through diffraction. So there's several things going on here. It's a very noisy image. There is no aliasing being done. It's pretty much just running a simple Monte Carlo code and finding what the rendering is. Same thing as you start getting more complicated geometries. So instead of looking at spheres, you start looking at people or trees or clouds, or in this case, a Buddha statue. One of them is marble, the other one is glass. It started getting more and more complicated as you move into more sophisticated objects. So these are going to end up being expensive, and people don't really want to deal with too many expensive things. On top of this, what happens if you have a translucid material? So not only you're going to have your rays getting reflected directly from the surface of the material. You're also going to have light penetrating in the subsurface, right? So that's what happened in translucent materials. That's what happens in the skin. And theoretically, what you would do is you would follow these paths and see how much of these energies end up getting deposited at that point and contribute to this ray that's going to go to your camera. Thing with that is too expensive. Back about 20 years ago, when people started looking into this, they didn't have the computational power to go through that kind of system. So what they did for subsurface scattering was a sort of diffusion model. One of the seminal papers is this one, Practical Model for Subsurface Light Transport. And what it does is literally it's getting the light source to this point, and then is going to use a diffusion approximation to say how much of that energy is deposited into this point. So that makes it much faster to run. Here I have some examples from that paper. To give you an idea, this is a Monte Carlo simulated one, the one on the right. That one took about 1,200 minutes to be complete. The one in the middle is the one that they're proposing in this paper that does a single scatter step. That's just one scattering, one bounce of the light, and then uses a diffusive model. And then there is another correction term, which is this F term here. But they end up getting this image, which is pretty similar to this one, in about 5 minutes. So that was pretty good. But because you're doing a diffusion approximation in a sense, there are some kinks, right? There are some things here that you want to be able to get rid of. For instance, if you have curvature or if you have a little hole in your system, that fails, right? Because it's just going to spread out that energy towards here, and it's not going to see this little corner. It's not going to be able to see it. So it's going to smear that information over a part that should not be smearing. So what happens to this? What kind of example do we have? Going back to the skin application that I mentioned, and I hope in the projector you'll be able to see the difference. It's usually better in the monitor, but I hope you're going to be able to see something here. Right there under the nostril, it's very pink there. There's some extra energy being transported from the nostril into that part. It's going to be more obvious after I showed you the comparison, but pretty much what's happening here is that issue that I just showed you before. You have a diffusion code that doesn't really see that curve. So you need to deal with that. Thankfully, as computer power evolved and people could do more sophisticated calculations, they started abandoning that kind of diffusion model and started looking more into ray tracing, say Woodcock tracing. So that is pretty much what you do in Monte Carlo, right? All you are used to seeing this in Monte Carlo calculations. You're shooting a ray from your camera to the surface. You're allowing your Monte Carlo software to bounce that particle around. Eventually, it's going to come back to the surface. If you can trace a ray from that point into the light source, you got one sample. But if you can't, you kill it. So that simple step is going to get rid of that smearing, because if I get my particle up to here and there is no direct line from the surface to the light, it's not going to be a sample in my calculation. So that did a pretty good job. So this is the diffusion one that I showed you before, and I'm going to flip them back and forth, and I'm going to point out some differences. But pay attention to close to the nose and up here around the eyelid and the eyebrow, and you'll see the difference into that. Pores get a little more easy to see. The light around the eyelid and the eyebrows, and that extra energy that was deposited around the nostril is not there anymore. Like, it's there now. It's a little pink, and then it disappears. So that did a good job. You can also do anisotropic path tracing, so do some biasing in it, and that also gets rid of a little bit more effects. This one is harder to see in the projector, but even though it's very subtle, this is usually what makes or breaks animation, right? Makes or breaks something that's believable and visually pleasing. So what the problem then was is how can you improve into that subsurface scattering? How can you improve into that kind of imaging? So what I'm going to talk to you about today, we already did the introduction, so we're done with that. I'm going to give you an idea what I mean when I say non-classical transport, which is this area of research that I've been working in the last few years with several different applications. I'll show you some 1D results just because they're easier to plot and easier to see the effects. And then we'll go back to this CGI question. All right? So, non-classical transport. I've been throwing this word around a little. When you have, say, an atmospheric cloud with water droplets, and you have photons of light coming through your cloud, you are in a stochastic medium, in a sense, right? You don't really know where your water droplets are, where air is. And turns out back in the 90s, late 90s, early 2000s, the atmospheric community found out that the exponential decay law that people are used to in transport, so the Beer law, doesn't really apply to the decay of these photons traveling through atmospheric clouds. In fact, they end up with some sort of algebraic decay that may not even have a second moment. It may diverge. In which case, you cannot use diffusion. You have something they call anomalous diffusion. So it gets way more complicated. So when we say classical transport, which is what all of you are used to see when you work with the Boltzmann equation, basically what you're saying is that you have a material in which the colliders, the places where the particle is allowed to interact, are Poisson distributed. So you have no spatial correlation in there. Your particle can just freely bounce around. And if I were to plot a histogram of these distances between collisions, you end up with an exponential decay. The random walk that you end up with, it's a Brownian random walk. It looks like Brownian motion. And the probability function for these distances between collisions is the exponential decay you're all used to. That gives you the Beer law. But how do you build then a system in which you have non-classical transport when you homogenize it? So let's think about this. You have one clump, and in this one clump you have Poisson distributed colliders. So that could be a water droplet, and inside this one piece of material, you have Brownian motion. Everything works as you're used to. But then I zoom out, and I look at the global system. So the global system now is a lot of those clumps. Each one of these is the previous figure. And a particle that is traveling now between these clumps is going to have these large jumps going from one into the next. And the histogram is not going to be an exponential anymore. It's going to have a peak for these large jumps in S. So how can you deal with this since this is not an exponential function anymore? First of all, what I just described to you ceases to be a Brownian random motion. It's now a Lévy flight, which is a different kind of random walk. It looks like that. And this has applications in a bunch of different areas in Lévy glasses, astronomy, foraging hypothesis. Turns out sharks, when they're looking for prey, that's how they hunt. They don't just start into increasing circles. So there's a lot of different applications for that. But the point is, if I try to homogenize this system with the Boltzmann equation like we usually use, you're going to inherently be assuming that the homogeneous system has an exponential decay. And what I just showed you is that that's not necessarily true. So we need to have a different tool that can capture the kind of system. Where are the applications for this? So water droplets in a cloud is the one that I used to make this example. But as you can see, when we move into the nuclear area, this is also the kind of system you have in a pebble bed reactor. Instead of water droplets, you have fuel pebbles. Instead of air, you have a coolant gas, say helium. And you have some sort of low granular flow going through the system. The other option would be a boiling water reactor. Now you're flipping the optical thickness of your system, and you're going to have water and steam bubbles. And again, in space, these are all stochastic systems that all have the fundamental same mathematical treatment. So that's how I got interested into this. So came from early 2000s in the atmospheric sciences, and then slowly trickled into the nuclear awareness. So how do you deal with that? I'm a mathematician, like was said, so I'm not going to walk you through all the derivation, but I'm going to give you the key points of this. And here is the main assumption. So in classical transport, you're saying that the probability that a particle will collide depends on your total cross-section and energy, but it's independent of how far this particle has traveled since its previous collision. It has no memory. That's basically what you're doing in any transport calculation you've done before. The change that we're proposing, and the change that is the birthplace of this method, is in saying that the probability of collision is going to be also called a sigma t, even though it doesn't really mean a sigma t, it's some sort of mathematical artifact, is going to depend on that s. And if it is going to depend on that s, you can have a general probability function, given by this function here, that is not necessarily an exponential. If sigma t is not a function of s, you can see that this guy here reduces to the exponential we had before. So the classical transport is a particular case of this. But in the case of non-classical transport, this PDF could be any probability distribution function. And you would be able to do a transport code and a transport approach to any of these heterogeneous systems that are now homogenized in a new system that preserves that global PDF. So that's what we're looking into. So now I'm going to use my mathematician prerogative, and I'm going to say it's easy to see from here that you get that. All right? And I'm going to explain that equation to you, but I'm not going to show the steps in between. So that's top one. The top one is the non-classical transport equation. The bottom one is the equivalent classical transport equation that you're used to see. I'm making a few simplifying assumptions that don't really take anything away from it. I'm assuming steady state, monoenergetic, isotropic scattering, isotropic source. But other than that, they are doing the same thing for different systems. For instance, you have your streaming term here. You also have your streaming term there. You have your collision term. Sigma t now depends on s. You have your collision term. You have your in-scattering source and your internal source. They are here too. In-scattering source, internal source. But there is one thing that is different. Besides sigma t now depending on s, I also have an extra rate of change in there, which makes this whole equation look very much like the time-dependent one, right? And if you want to, you can think of it as a time-dependent equation if you think of s as a pseudo-time variable. Instead of saying this is the distance between point of collision to next collision, you could say it's the time spent between last collision to next collision. So it's fair to say this is sort of a pseudo-time dependent equation. The other oddity is the right-hand side now has a delta function. What the delta function is doing is resetting that value of s every time a collision happens. So when a particle is born, it has to be born with s equals 0. So it's in front of the q. When a particle collides, the value of s, representing distance traveled since previous interaction, gets reset to 0, because now this one is my previous interaction. So in this case, you can write this whole thing as an initial value problem, if you wish. The left-hand side equals to 0, and then an initial value on s, which is going to be the right-hand side of the equation. So there's different ways to think about this. Now, you can show different things with this, and I'm not going to go into all of these details, but you can show that it has an integral equation form. This integral equation form is going to have a probability function inside, and different choices of that probability function are going to give you different results. If I choose an exponential and I plug it in there, I end up with classical transport. If I choose this one, which needs some deriving to do, then I get diffusion, exactly diffusion. If I run a Monte Carlo code with this probability function here and sample from that, I'm exactly reproducing the solution of the diffusion equation. And you can do that for sp2, for sp3. You can do that in different ways. You can also use asymptotic analysis to derive non-classical diffusion equations. So This is the classical diffusion model for the previous problem I gave you. This would be the non-classical. Now, this bracketed S and bracketed S square, those are the mean free path and the mean square free path of this non-exponential PDF. If it is an exponential, the top one reduces to the classical one. So it all works. It's all a generalization. I can keep going, and I can show you other ways to do this. But specifically, what's the catch, right? Because I'm doing something a little more complicated. I'm extending my phase space. I'm introducing a new independent variable. What's the catch here? The catch is that you really can only solve this if you know that guy. It's not necessarily an easy thing to do. You do know it has a direct relationship to the PDF. So if you have a way to analytically calculate the PDF, which has a physical sense that everybody knows and understands, you can get that sigma t of s. Otherwise, you can try to get the p of s experimentally. You can try to get the p of s by doing simulations in Monte Carlo. But it would be nice to have an analytical solution for that. Remember, p of s is just the probability function of the distances between collisions, so it has a physical sense. The sigma t of s is harder to grasp. I'm not claiming that sigma t of s is a physical quantity, because if you think about the definition of total cross-section, what that would be saying is that the material knows how far the particle has traveled, and it changes its density according to that. Right? That cannot be true. But mathematically, this is preserving the PDF that I want. So that's why I use it. And in the limit in which that is an exponential, that sigma t reduces to the classical definition of total cross-section. So what I need to do is find different ways to find it, what that p of s is, what the sigma t of s is. So I'm going to show you some 1D results, because they're easier to follow, and to give you a visual of what they're going to look like. So for this case, I have a 1D random periodic media. What do I mean by random periodic? So I have a periodic media, and I randomly place my origin in there. So at any time, I can close my eyes and point and say that that's going to be my origin, and then that's going to fix where I have solid and voids. But before that, it's a random system. So I can do that and define the thicknesses, define what the probabilities are. I'm going to have a cross-section for the solid. It's a void for the void, so the cross-section there is 0. I can analytically calculate what this p of s is going to be, and it's going to be angular dependent because I'm in slab geometry. In the case of classical transport or just volume average homogenizations, you're going to get something that looks like an exponential, just to compare against what people usually do. This is the actual PDF for that problem. It looks harder than it is. It's actually quite straightforward to get this analytical solution. We're going to be looking into this case here in the middle, in which the thicknesses of each one of the materials are the same. So you're going to have this probability function. Now, I want you to think of what you expect the PDF to be, right? Usually, for a homogeneous or a heterogeneous system, you expect your PDF to be a nice decaying function. Right now, because I created this random periodic media, it's actually going to be something like this. That's my PDF. If I'm looking into the mu equals 1 direction, and for sigma t equals 1, and the thickness is equal 1. So that PDF, even though it has sort of an exponential decay in each one of these steps, it's kind of jaggedy. Right? It's not going to give you the same result. If I look at the log scale, this is the same graph that I showed you before. It should come down all the way to 0, but there is an artifact from MATLAB here. But that's your PDF. And that is going to translate into a sigma t of s. Right? If you're just doing a volume average of that system, your sigma t is going to be a constant. It's going to be 0.5. But in this case, your sigma t is going to look like that red line. And you can think of it from a physical point of view. What does it mean? If a particle is born or scatters somewhere, I know it has to be the solid. So I know that at that point, the cross-section is 1. As I walk away from that point, the probability that I'm leaving the solid and going to the void is going to increase. And the cross-section is going to start approaching 0. Because it's periodic, exactly 1 thickness away from that point, I know I'm going to be at a void. So that's why it goes to 0 there. And then I start doing the other way around. I'm going to start approaching the solid, if I walk exactly 2 thicknesses away, I know I'm back in a solid. So it goes back to a 1. So this is physically very easy to understand. And the question is, what does the solution look like? So I did a little simple test problem here. Vacuum boundaries, isotropic scattering, scattering ratio is going from diffusive all the way to purely absorbing. And just to see this periodic waves, I put a source just in the center, not throughout the whole system. So if I do that, that's the correct solution. That's the benchmark. So there are 2 things that I'm interested in capturing with the models that I would use. So this is done by brute force. This is done by creating enough of those realizations and averaging over all of them to find out what the flux is going to be. So there's 2 things I want. I want to be able to capture this peak in the middle, and I want to be able to capture the shape, or the general shape of this decay. If I use atomic mix, other kind of bias, volume averaging that people usually use, this is going to end up overestimating the peak, and it's just an exponential decay. It's going to smooth out this function. You're not going to capture this wavy behavior. If I use that sigma t of s that looks like those up and down jaggedy function, that gets me the peak right on top, and it also captures this wavy behavior of the solution. So this is all done for scattering ratio 0.1. But if I move forward, these are going to be the relative errors as I go from diffusive to purely absorbing. Now, for diffusive systems, atomic mix is known to be fairly accurate. But as I increase absorption, you see that the atomic mix error increases, and the non-classical error decreases. So this is a relative % error. 0 here is that peak, and 10 is as you go away from it. It's a symmetric problem. So what can we do? So there's 3 methods and tools that we usually use, right? We use Monte Carlo, or you use deterministic codes, or some sort of hybrid code using both of them. The thing is, for both of these cases, you are going to need either the total cross-section or the PDF. If you have the PDF, you're going to be using the same Monte Carlo code that you have, but you sample from something that's not an exponential. If you're using deterministic, you're going to have this sigma t and find out how you're going to discretize your system now that you have an extended phase space. So it comes to the whole point, and I'm going to not give you all this math here, that one of the approaches that we're working on right now with people in Brazil is how can you use current deterministic codes to solve the non-classical transport equation. So one of the options is I can expand my s variable using Laguerre polynomials. And if I do that, I get a spectral representation that's going to have the Laguerre moments. And for each one of the Laguerre moments, I'm going to use any transport code that you already have. So in the end, I'm going to have some equation that looks like this. And any deterministic code that you use for regular transport is going to solve that. M is the Laguerre moment of order m. So you're going to use this for as many Laguerre moments that you want. And just to show you what the results are, so again, the Laguerre sum is going to need to be truncated at some value. There is an improper integral that can be done analytically, but you can also numerically solve it. Any traditional code is going to solve this problem, but just looking at the same kind of problem that I showed you before for the 1D, these are what the errors look like comparing to a benchmark. So the red one is m equals 50, is the order of the Laguerre expansion. The other one is 200. So for a purely absorbing system, you need to go higher in order to capture the behavior. As you get more and more scattering, it doesn't really solve so much of your error here, even though you're still in the 0.4, 0.5% error. So these are just to give you some general idea of what's going on right now. And the questions that we have, what happens if that non-exponential function has a fat tail, if it has a truly algebraic decay? If it has a truly algebraic decay, it might not even have the second moment. Diffusion might not apply at all. You might need to go into fractional calculus and use a fractional diffusion equation. How does this result look like if you do that? Can you use acceleration techniques? So we're working on this right now. These results here are just done using regular SN equations as source iteration. But you can accelerate them. You can use DSA. You can use NSDA. You can do a P1 acceleration because you have to accelerate each one of the Laguerre moments independently. But it's easy to do that. Will coarse mesh methods help? Probably. We're looking into that right now. But we still need to do a full convergence analysis. And we need to investigate how difficult this is going to be as you move into multidimensional problems. I do have results for some 3D stuff, but most of them are diffusion-based. What other things are we doing? So I showed you that integral equation. Turns out that with that integral equation, you can obtain a PDF that is going to represent the Levermore-Pomeranian equations, which is this other class of equations to deal with heterogeneous medium. The problem with running Levermore-Pomeranian equations for diffusive systems is that it gets really expensive. So just to explain what you're looking at this table here, so this was a project with Livermore that we presented last year. These are the benchmark results. These are LP Monte Carlo, and these are non-classical Monte Carlo. They're all sort of the same order of error. But this is how much wall clock it took to solve them. So we're reducing the time by 3 orders of magnitude by using a non-classical approach. Is this going to be good every time? It's going to be good for diffusive problems. It takes away from some of the attractiveness of the LP equations, which give you different fluxes, expected fluxes for each material. But in the future, we hope it might be used to accelerate Monte Carlo codes for LP equations. So it's possible that we can use this sort of algorithm to accelerate Levermore-Pomeranian algorithms in order to get faster solutions with that system. Now, these are the collaborators that are working on some of the results that I showed you here today. So they're my friends at Rio, my students at Ohio State, my postdoc when I was still in Berkeley. So Rachel, Patrick from Livermore, Magnus from Pixar. These are our sponsors, Nuclear Regulatory Committee, the Brazilian Ministry of Education. We have a whole project with them that has a logo and everything. It looks really nice. But I want to, before we finish, go back to that subsurface scattering problem that we discussed. So there is one more thing that they want to make better into this kind of problem. And that is what they call bleeding. So if you remember when you're a kid and you would play with a flashlight behind your hand and it turns pink because you have more light going through it. So that's what they want to be able to capture. They want to be able to capture enough light penetrating deep into a translucent material. But they also want to preserve the short scatterers. And up until this point, they're using exponential flights. If you want deep penetrating light, you're going to have to increase your PDFs in such a way that your mean free path also increases. And you lose the short scatterers close to the surface. If you don't lose the short scatterers close to the surface, you cannot have enough light penetrating deep enough. So you need to be able to balance that. So it turns out that with this non-classical equation, you can look at it from a transmittance point of view in the atmospheric sciences. And this was done a few years ago by one of my colleagues, is Anthony Davis at JPL, Jet Propulsion Lab. We have a project together. And you can get that non-classical equation and show that if you have something that looks like an algebraic decay, you get a parametric transmittance equation that's pretty easy to work with. Specifically, that parameter A in there, the larger it is, the closer to an exponential you get. The smaller it is, the more algebraic that decay is going to be. So it gives the artist this one little parameter that they can tune and change the bleeding however they want. So if this is an algebraic decay, because you have a fat tail, you're going to be depositing more energy into that tail of the PDF, but you're still preserving the mean of that PDF. And it can be a short mean. You're still preserving the single scatters and the short scatters. As you tune in that A, you get more or less bleeding. So this is with A equals 10. This is pretty close to the exponential one that I showed you before. There's pretty much nothing being gained here. Again, I don't know how much you're going to be able to see with the light in the screen, but as I move from A equals 10 to smaller values of A, the skin is going to be more pink, and you're going to have more of that bleeding transparent effect in the skin. So going to A equals 3, I think there's not much you can see at this moment from the screen. Trust me, in the projector it looks great, right, in the screen. I'm going to go one more, and maybe that's going to be sort of. If you really look close to the nose at that corner there, you're going to see it's going to become a little pinkish. Yeah? Kind of? You're being nice. Thanks. It can be too far, right? I can go up to approximately 1, and then it starts looking like a wax figure, which is bad. But the point here is, as the artist has the option to go in and change from, this is a little faster. Maybe that's easy. Oh, if you look at the nostril, you can see it. You see the nostril? So this one in the screen looks really fake. It looks like a wax figure. These ones are more subtle, and you can start seeing around the nostril how much bleeding you have. And this has to do with the long scatters penetrating, but the short scatter being preserved. So is this physical? No. This is not really what happens in the skin when you're throwing light into it. But what these guys are interested in is not so much, is this physically accurate? They're interested in, is this visually pleasing? Is this look realistic enough and not creepy that I can use and put it in a kid's movie? Can the director get enough information that I can tune in and do a fine-tuning into this? And usually this is what breaks or makes a new CGI breakthrough. I'm going to give you an example how not physical this is. I organized a section of the CGI people at one of the transport theory conferences a couple years ago, and we had other people from Disney Research and Pixar giving talks, and we had the team that did Cars from Pixar. You all remember Cars. All the light scattering in that movie is pretty physical, and as you know, cars are metal, but those ones had eyes in the windshield, right? So what happens if you have metal right in front of something? It gets reflected. And it looked horrible because it looked like all the characters had 4 eyes, because they have the 2 eyes in the windshield and then the 2 eyes again in the hood of the car. So that kind of physical code works for you to get an accurate result, but it doesn't necessarily work for what they were trying to do. So they have to go in then with the director and the artist and sort of tune out that physical enhancement and take away that extra pair of eyes, or at least tone it down from the hood of the car. So all of these little tune-ins that they're looking into is really what's making the breakthroughs in CGI and animation. And I said that this was 2015 when Magnus first contacted me. And if you look at the CGI community now, they pretty much took this and ran away with it. There's a lot of papers now coming up in the subsurface scattering and how you deal with a new transmittance function in non-exponential flights. And they don't have to worry about blowing anything up if they get it wrong. So it works pretty well. They have way more money than we do to do movies and video games. There's new anti-aliasing video game material that if you're into it, you'll see the fog and the light going through mist that is all done now. It's starting to use non-exponential free flights to try to get that. And I just wish that I had more of a foot in it to maybe also get a Technical Achievement Academy Award. But at this moment, I'm just living by proximity with the actual people doing it. So this is pretty much what I had for you today. I think I'm about on time, 45 minutes. So thanks again, and I think I will take questions. And the one on the left was the original diffusion one that really did not do a good job. And if you remember those CGI movies back in the early 2000s, they all looked too bright. All of those materials, the surfaces look a little too bright. So they use marble, they use bone, they use translucent crystal and milk and other things, and they're already having that on the papers that are coming out in SIGGRAPH right now. how far are we from doing this at a scale of animation? I'm not sure.
Questions?
I have a question about of the things you've learned from doing some of these simulations for movies and such. Have you been able to bring something back to nuclear engineering from what you've learned?
So that's the idea right now. At the moment, we sort of, at first, there is a communication issue between what we call some things and what they call some things, right? So there is that first barrier. Once that is gone, they started looking more into the non-exponential flights as transmittance. And now they have some really good results on how to deal with interfaces. So one of the things I did not mention during the talk is how do you deal with boundary conditions and interfaces on that S variable, right? It's not as easy as it would look. If you have vacuum boundaries, sure, nothing happens. But if you have an incoming particle from a different material or a different region, and you have to deal with interfaces, how do you preserve continuity? How you deal with that extra phase space? So now they are doing something really interesting on the transmittance function that they have on the interface. It's not completely physical, but it's a good turnaround that we might end up implementing in our calculations. Mm-hmm.
Any other questions? Okay, let's thank Dr. Vasques one more time.
Thank you very much.
And as you know, we have refreshments afterwards, so feel free to join us down in NEB 200. Thank you.
Thanks again.
It's a good seminar because it really gets people thinking a little bit outside.
Right.
The whole thing. It's interesting.
That was the point. I'm glad people enjoyed it. So, see, I had 67 more on backup.
I see that.